Hey, it's Mr. Shrum, and I'm on the Scientific Models and Measurements tutorial, and I'm going to walk through the lesson activity and help you all um, through the model and answering the questions afterwards. So here we go. This whole lesson is about comparing scientific models, and we're going to use these types of models to give physical accounts of phenomena, things we experience in our day-to-day lives, and then move flexibly between the models. So we're going to model with math and then look for and make use of structure. So here we go. It'll make more sense once we get going. So we're going to observe and compare three models, and we're going to look at friction. And friction, right, if you want to look things up on your own, this is the resistance that one surface or object encounters when moving over the other. It's when they rub against each other and they sort of conflict sometimes. And you can measure how much friction there is, the force of the friction, by this equation here. So for the first model, we're going to launch it. Can you see that? Okay, so here we have two books. We have a green physics book, a yellow chemistry book, and then if you zoom into that tiny space, pretend we're zooming in so much that we're seeing these individual particles. So here we go. We're going to start rubbing. Okay. So what do you notice? You see the particles are vibrating. There's temperature as well. Temperature usually means some type of, oh, there it goes. Okay. So there's that. Model 2 kind of shows the same thing in a different way. Here's a box. Here's the ground. And to calculate the force of friction, we will use F equals, this letter is called mu. Mu that didn't work. So here we go. We'll use all right, so here we can explain the coefficient of friction. Friction is a force which holds back the movement of a sliding object. So when we slid those books together, there was a force between the particles of one book against the other. And the force acts in the opposite direction of the way an object wants to slide. So if we slide something to the left, the force will push it the other way, push it to the right. So we move, rubbing something to the left, the force of friction will be going in the opposite direction. Besides, the coefficient of friction is a very important term here. And it's represented by the equation F equals mu times N. No advertisement, thank you. So another way to think of friction is resistance. when you push something heavy on concrete and you can kind of feel it push against you, um, that is friction. And the coefficient of friction is determined by the material you're rubbing against. So if you're on concrete, it'll have a very high coefficient, which means there will be a lot of friction, whereas something less hard, more slick, like tile or a gymnasium floor, you can slide things on them more easily than concrete. And here's the equation. F equals N. N is the normal force. Let's go back here. The normal force is the opposing force to gravity. So we have gravity pulling down on the box, but in order for the box to stay in place, there is a force pushing upwards to keep it in balance. And when we push something to the left, there will be an opposite force of friction applied to the left. And we can find the force of friction by multiplying this coefficient that we can find in a list or table. And then the normal force is just this, N. So in part A, a scientific model is a representation of a concept that makes it easier in some way to understand and use. Which of the models represent the force of friction? So we have this model, model 1, which is like a simulation that you can interact with. Model 2 is a picture that labels all the forces and shows you the contact area. And then model 3 is a mathematical equation, and they all work together to give you a better view of what we're doing. And they are all different. So simulation, a picture, and then a mathematical equation. But they can help people understand different aspects of a phenomenon. Let's keep it unanswered for now. Drag the correct tiles to the boxes. You will not use all the tiles. So we definitely know the last model 3 is using math. That looks like an equation. Model 1 is virtual. If we were in class, we would, use a physical model. But for now, we're using this PhET simulation. And then we have a conceptual model, and it labels the forces and tries to explain the phenomenon visually, conceptually. So we have an online simulation, a form of a diagram, and a form of an equation. Okay, so we're going to describe the correct type of model with the appropriate words. Okay, so a conceptual model provides simple visual understanding. And by diagramming the forces involved, model 2 gives us a simple visual understanding of the forces and their directions. It also shows the roughness of the surface in contact, giving us a more visual understanding of how these surfaces interlock. A virtual model is dynamic and interactive. It can provide a molecular understanding, or a molecular level understanding rather, of a concept. Model 1 is a virtual model, and it shows how friction affects these surfaces under various conditions. Model 1 also shows what happens to the surfaces at the molecular level. A mathematical model involves a numerical prediction. Model 3 is a mathematical model. So if you look at it, it's something equals something else. So F, the force of friction, equals the coefficient times the normal force. Because it is an equation, you can enter numeric values for the normal force and the coefficient of friction, and the result is a numerical prediction of how strong the force of friction will be. So they all have their unique purpose, and they are all useful to scientists everywhere. So we'll go through, oh, here's another question. Sort the length measurements in increasing order of magnitude from smallest to largest. Another big section of this lesson is the scale of what you're measuring. So here, I'll just explain with the answer key. So we have the smallest being nanometer all the way up to kilometer. And I'll go back to the slide with the prefixes. And all you really have to do with these prefixes is you'll memorize them over time, but it will start with the base unit, a meter, 1 meter, and then the prefix will either say it's a magnifier or a minimizer. So decameter is 10 meters. Hectometer is 100 meters. Kilometer means 1,000 meters. Megometer, I guess you would say, is 1,000,000 meters. Giga, billion. And then to go the other way, so if you're starting with 1 and you want to say 1/10 of a meter, you say decimeter. Centimeter is a 100th of a meter. Millimeter is a 1,000th of a meter. Micro, nano. So you see how nano's all the way down here. Micro, milli, centi, deci, deca, hecto, kilo, mega, giga. Talking more about tools, how to use them, scientific notation makes it easier to write numbers. Oh, and this is a good one. This is a good example of, so if something has a lot of zeros, it's way easier to write this 3 times 10 to the 8th. And you're just moving the decimal place 8 times to the right, starting with 3.0, and then bam, 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 bam. And you can also write decimals with a lot of zeros, like this as well. And anytime it's 10 to the negative power, you're moving the decimal place to the left now. So if it's 10 to a positive number, you're moving the decimal point to the right. A negative number, you're moving it to the left. And here's another way to visualize it. 3 times 10 to the negative 4 is also the same as 3 times 10 to 1. 3 times 1 over 10 to the 4th power. and that gets you 3 over 10,000, and then you get 0.0003. And here's another way to explain it. And there's another visualization. So 4.15 times 10 to the 11th. So you can start from 4.15 and then move 11 times to get a bunch of zeros. And then 5.7 times 10 to the negative 12. Start with 5.7 and then move 12 times to the left. Okay. Easy peasy. Here's more dragging. 0 is the smallest amount. Then you get a very small number, slightly less small number, and so on until you get 3,100,000 meters. So this is practice for writing out the scientific notation. There's more examples of writing scientific notation. And once you get used to it, it's not too hard. I say just practice with these in the tutorial and then the mastery test. And over time, you'll get used to this scientific notation. But that's all I have for you today. And I'll upload this to Canvas. And if you have any more issues, let me know, and I will go through these lesson activities. All right, see you guys later.